Here we are in 4.06, sequences. You'll see in this example here we have crimes and then tourists, and Detective McMurlock is trying to figure out if there's any kind of a correlation between the two. So you'll see the months for both crimes and tourists will go up by 1, so +1, +1, +1. And then we kind of have to see what's going on with the crimes and the tourists. So for the crimes, you've got 200 to 180 to 160 to 140, -20, -20, -20. So there is a pattern that's happening here. It's decreasing by 20. And anytime you're adding or subtracting, that counts as something that we call linear or an arithmetic sequence that we'll talk about a little bit later. So you'll see for the tourists, we've got +1, +1, +1 as well. And then for the months, and then for the tourists, we're kind of going to see if we can find a pattern. We could try +10, but then 20 plus 10 does not get us 40. So what we're going to have to notice is that it's actually going to be times 2. So 10 times 2 is 20, 20 times 2 is 40, 40 times 2 is 80. And just to repeat what I said initially, adding or subtracting is going to be a linear function, that's going to be arithmetic. However, when you're multiplying, so for example times 2 times 2 times 2, that's going to be something that we call geometric, a geometric sequence or an exponential function. So what it's asking us is, are they both linear? Actually, that's not going to be true. They're not both linear. The only one that's linear is the crimes one. So the correct answer is the tourist function is not linear all the way to the right. Here on page 2, we have our first kind of talk about sequences where we have honeybees and they're talking about a honeycomb. So initially right in the middle you've got just one honeycomb, okay? And then as this honeycomb kind of expands and keeps on growing, you'll notice that there's going to be a pattern for each of the rings. So for my first ring around the middle, there's going to be 6 different honeycombs. And then as we keep going, the second ring around is going to actually be 12. So if we count that up, it's going to be 12. And then if we keep going further, we can actually think of a pattern here. But if we go to the third one, we will find in the third ring that there are actually 18 honeycombs going all the way around. So we start with kind of just 1 in 0 in the middle. 0, it doesn't really count as a ring because it's in the middle. So we have 0 in the middle, we have 6 in ring 1, we have 12 in ring 2, and then we have 18 in ring 3. Then underneath the honeycombs, the lesson starts talking about explicit and recursive formulas. The explicit formula is the one that we mainly talked about together in class when we did this. And this is where we can generate any term in a sequence. So I don't care if I'm looking for the 4th term, the 5th term, the 629th term. All I need to do here for the honeycomb is take the number 6, which was the number in the first ring, and then just multiply it by whatever ring I'm trying to find. So if I want the 254th, I would just take 254 times 6, and that should give me the number of honeycombs in the ring. Now the question says, how many cells will there be in ring 7? So I'm just going to take 6 times 7, and that's going to get me 42. So explicit is to find any term that you can think of, but recursive is a little bit more particular because in order to find the term that you want, you have to use the term previous to it. So let's say you want the 17th term, you need the 16th term. If you want the 564th term, you need the 563rd. So it takes a little bit longer to work through that. So for example, if you want first, second, third, in order to get to 600, you need 599. So it's a little bit harder to work through. Now when we're talking about using a formula, we can see that it says f of 1 is 6, meaning that in the first ring we have 6 honeycombs, and in order to use the formula, we want to take f of n, which stands for any term, is going to be equal to f of 1, which we know is 6, plus f of n minus 1. F of n minus 1 represents the previous term, okay? So I'm plugging in 6 for f of 1, and then plus the f of n minus 1. So my question is the same. It says, how many cells will be in ring 7? Well, in order to figure out how many cells or how many honeycomb, whatever you want to call it, is going to be in ring 7, you need the previous term. You need ring 6, which I don't have. Can we figure it out? Sure, but it's going to take us a while. So then in order to get f of 7, we need f of 6. We need the previous term in order to make a recursive formula work. And in my opinion, if you ever have the choice, don't use a recursive formula. It's probably going to take you too long depending on what you're looking for. Definitely go with the explicit formula. It's going to be a lot easier. No matter what term, any term that you want to find, you can easily use the formula, plug it in, and figure it out. So at the bottom of this page, we have a couple practice questions. So you'll notice here we have a sequence. We have 7, then 14, 28, 56, 112, and 224. What I'm going to suggest that you try to do is anytime you can make a table to organize it for yourself. My x values are going to be just the number of term that it is. So term 1, term 2, term 3, term 4. Term 1 is 7, so I wrote 7 under it. Term 2 is 14, term 3 is 28, and so on and so forth. It's asking us, is this sequence considered a function? We have to figure out whether it has any sort of a pattern. We also know that in order for something to be a function, we cannot have two outputs for the same input. I cannot have two different y's for the same x value. So if I try to find the pattern here, I could think, well, 7 plus 7 is 14, plus 7 is 28. That doesn't work. You'll notice that there is a pattern of multiplying by 2, so times 2 times 2 times 2. So is this a function? I would definitely say yes, because every single x value or domain value or input value has one and only one output, aka y, aka range, aka f of n. Those all mean the same thing. They also went a step further in the answer and wrote out the explicit and the recursive formulas. We'll do a little bit more with that later on. Alright, so example 2 says a tree farm starts with 100 trees. Each year it sells 30% of the trees and plants 50 more. How many trees will be growing at the end of each year? So use the recursive formula to complete the table for years 3 through 6. So in our recursive formula, we have f of 0 is 100, so that's our starting point, and it says f of n equals 0.70 because we're taking 70%. So if we're selling 30% of the trees, we're keeping 70% because the total would be 100%, times f of n minus 1 plus 50 that they're planting. So all I'm going to do here is I'm going to start plugging numbers into the formula. So I'm going to start with my 0.70 times f of n minus 1. So what that means is if I'm looking for the third year, I need the one before that. So if I'm looking for the third year, I need the second year, and then from there I'm going to add 50. It was at this point that my screen recording kind of cut out a little bit, but what I want to do is take 0.70 times the previous year, so from year 2, which is going to be 134, and then plus the 50. So don't forget to multiply first and then add 50. That should get us 144. After that, when I want to go ahead and do year 4, the previous year from year 4 is going to be year 3. So 0.70 times the 144 plus 50 should get me a total of 151. Then for year 5, I'm going to follow the same exact process but using the year previously, so 151 instead of 144, and that's going to get me a total of 156. And then last but not least for year 6, I'm going to follow the same process again but use 156 because that was the year previous. That's what recursive is all about, is the year previous, and we get 159. Alright, so last question, question 3. So question 3 talks about a very famous sequence called the Fibonacci sequence. Some of you may have heard of it, some of you may have not, but the Fibonacci sequence essentially, it starts with the number 1 and then 1. So it's 2 ones in the beginning. And then from there you take the current term you're at plus the previous term to get the next one. So you take where you're at plus the previous to get the next one. So before I get to the sequence, I want to try to label this as correctly as possible. So the first one we call f of 0, that's our beginning, and then the next term would be f of 1, then what I haven't found yet would be f of 2, then f of 3, f of 4, so on and so forth. We label it that way because it's the first term in the sequence, the second term, the third term, the fourth term, the fifth term, so on and so forth. Now, when I'm actually going to go ahead and calculate this, I want to take where I'm at right now, which is the 1, plus the previous term, which is 1. 1 plus 1 is going to get me 2. After that, I'm going to keep going, and then 2 plus 1 is going to get me 3. 3 plus 2 is 5, and then 5 plus 3 is 8, and then 8 plus 5 is 13. 13 plus 8 is 21. 21 plus 13, so on and so forth. Okay, I believe they ask us only for the first 6 terms, so that's going to be the 1, 1, 2, 3, 5, 8. That's going to be my final answer for the Fibonacci sequence. Alright, so here we are on page 3. This is more of the same of what we did on the first page. It just does the work written out for us that we already did. So we have the crimes from Detective McMurlock or whatever his name is. The common difference here was subtracting by 20. That's a vocab word for you, common difference, because it's either for adding or subtracting, and then common ratio, another vocab word there, is for specifically when you're multiplying by a number. So we have the crimes was adding or subtracting, more specifically subtracting, and then for tourists it was actually multiplying, which is going to be for a geometric sequence. So at the bottom of the screen we have our very first set of examples to figure out whether something is arithmetic or geometric. So looking at sequence 1, we have our x values, which don't matter too much because, well, as long as they're going one by one. So for sequence 1 we have 1, then 2, then 3, then 4, that's fine. But we want to specifically look at the output values, so our y values that we have. So 5, negative 15, 45, and 135. I can tell kind of just by looking at it that I'm going to be multiplying by negative 3. Since it's multiplying, it will be a geometric sequence. For sequence 2, same kind of thing. I do want to try to find a pattern. It looks like they're going down, so it's either going to be subtracting or multiplying by a fraction. And just by doing some calculator work, I will notice that it is subtracting by, well, let's see, 120 to 95. Looks like it's subtracting by 25. So since it's subtracting, that will be an arithmetic sequence. For sequence number 3, we have a table form. That's fine. I'm going to look and see what's happening from term to term for my output. And it looks like I could tell it's just subtracting by 8 each time as we go through. That is going to be an arithmetic sequence. For sequence 4, same kind of thing, but something that you'll notice is that the numbers are decreasing a lot rapidly, more rapidly. So from 120 to 60 to 30 to 15. And then I'm just finding a pattern and noticing that it's getting cut in half every single time. So I'm technically multiplying by a half, multiplying by a half. The first thing I notice is from 30 to 15, but then I could check it all the way through. You can either write a half or you can write 0.5, depending on how you feel. It doesn't really matter. They are equivalent whether you write the fraction or whether you write the decimal. So since it's multiplying, that will be a geometric sequence. And then we have sequence 5. So it looks like Tony checked out 3 books, and then he checked out 6 books, and then he checked out 9 books. So if I write out the sequence 3, then 6, then 9, you'll notice obviously there's a pattern of just adding by 3, so that will be arithmetic. And finally, Linda made $9, and then she made 18, and then she made 36. The pattern here is definitely multiplying by 2, so this will be a geometric sequence. Here we are looking at page 4, which has to do with all the recursive formulas for arithmetic and geometric sequences. So you'll notice the formula there that we have does not include the first term, just the common difference. So pretty important to notice that we just have the common difference d, but we don't use the first term. Very similar to geometric recursive formula, where we only use the common ratio, we don't use the first term. So taking a look at our very first example here, I went ahead and moved it over to where I can write on it with just the graph. I just don't have the question, so you're going to have to bear with me for a moment. Something that you're going to see right off the bat is that we have 1, 2, 3, 4, which is normal for our x values, and then we have 6 to 12 to 18 to 24. So what I'm going to go ahead and do is I'm going to create a table. So I have my x's on the left and my y's on the right. And for my x's, I'm going to start with 1 through 4, and then I have 6, 12, 18, 24, like I was just saying on the right-hand side. Now what I want to do is I want to try to see what's the pattern, what's happening, but specifically for the y values. So starting from 6 to 12, it looks like to me is adding 6, and then adding another 6, and then adding 6. So my common difference, what I'm increasing by, is going to be 6 plus 6. So question number 1 says, is this an arithmetic sequence? I would say yeah, for sure, arithmetic, because we are adding. Okay, that's the definition of an arithmetic sequence, is that it increases or decreases by addition or subtraction, and this happens to be addition. Number 2 is What's the first term and what's the common difference? Well, the first term is 6 and the common difference is also 6. So that's what I have there. From there, for number 3, we have what is the recursive formula. The recursive formula is going to be f of n equals, we take f of n minus 1 plus the common difference. As you can see, I accidentally wrote f of 1, the first term. That should not be f of 1, that should say d for common difference. But luckily for me in this problem, the common difference and the first term were both 6, so it didn't affect how I did the problem. But make sure when you're doing the recursive formula that you use the common difference, not the first term, in case they're different. So there's my formula with f of n minus 1. And then question number 4 says to use the formula to find what it would be for the 5th month. Now keep in mind the recursive formula is all about using the previous term. So I'm going to take 6 plus f of 5 minus 1, because 5 is what I want to find. I want to find the 5th month. So then that's going to take me to f of 4. Luckily for me, I already know what f of 4 is. I don't really have to do a lot of work. F of 4 is 24. So I'm going to take 6 plus 24, or just 24 plus 6, and I'm going to get 30 for the 6th month. Now, looking at example number 2, what we have here, we have cars in a town and gas station prices, so for gas. So in the first month, we have $3. The second month is $3.30, and then $3.63, and then $3.99. It looks like to me that this is definitely not arithmetic, because from month 1 to month 3 it adds by 30 cents, but then from month 2 to month 3 it adds by 33. So that's already not a constant change. I'm not adding by the same number. So I'm going to check what it's going to be if I divide. And then it says what's going to be the price of gas in the 6th month. So the way I'm going to do this is I'm going to do the little, to figure out what I'm multiplying by, I'm going to divide trick. So I'm going to take the second term, which is $3.30, divided by the first term, which is going to be $3. And what I get as a result is 1.1. Now I'm going to take the third divided by the second, so 3.63 divided by 330, and that's going to also get me 1.1. And then just to double check the last one, I'm going to take 399 divided by 363, and that's going to get me 1.1 as well. Now from here it's asking me to find the recursive formula. So from what we were just talking about, we want to make sure that we use the common difference, or in this case the common ratio, because it's by multiplication, and then the previous term to find what I'm looking for. So what I'm going to do is I'm going to take the common ratio, which is 1.1, times f of n minus 1. So that's going to be the previous term. And what it's asking me to find is the price of gas in the 6th month. So I'm going to take f of 6 equals 1.1 times f of 5, because then we would just do 6 minus 1. But I don't know f of 5. I don't know the 5th month, so I kind of have to do an extra step. I need to go from the 4th month, find the 5th month, and then find the 6th month. So f of 5 is going to be 1.1 times f of 4, because that's going to be the previous month. And that's going to take me to doing 1.1 times 399, because that's what the price of gas was in the 4th month. And we get $4.39. And then finally, to find f of 6, I'm going to take 1.1 times what I got for the 5th month, which is $4.39. And I'm going to get my total for the 6 months, or whatever the price was for 6 months of gas, which is going to be $4.83. Alright, so next up we have our very first instance of talking about the explicit formula, which you'll probably remember from when we did in class. In this formula it says f of n and f of 1, but together in class we did a sub n, that might look familiar, equals a sub 1 plus d times n minus 1. So that's the formula that we did in class together. Whether you use f or whether you use a, it doesn't really matter as long as it follows the same pattern. So it looks like in the question we have a sequence that's 2, 5, 8, then 11. So in order to look for a pattern there, you'll see that it's increasing and it happens to be adding by 3 to get from term to term. Our common difference would be 3, so that's the number that we're adding or subtracting by, in this case adding. And our first term is just going to be the first term that we see, which is going to be 2. So my question says, what is the value of the 30th term? Well, in order to set this up, I want to take the first term, which we said was 2, plus the difference, which is 3, times n minus 1. But in this case, we're looking for the 30th term, so instead of n, I'm going to go ahead and plug in 30. So I'm going to move it over to the side a little bit. I get 2 plus 3 times 29, or 30 minus 1, which ends up being 29. And then I do want to make sure that I multiply first. So I get 2 plus 87, because that's what 3 times 29 is, and then I add to get 89. So the 30th term in this sequence, if I keep going, is going to end up being 89. Alrighty, and here we are looking at the geometric explicit formula. So same kind of thing, you might remember seeing it from how we did it in class, where we have, in this case, the sequence 3, 12, 48, then 192, and it looks like it's going to be times 4. So geometric is definitely always multiplication, and we want to make sure we check that all the way through. Now, this is the formula that they actually show you, but you should remember, hopefully, a sub n equals a sub 1 times r to the power of n minus 1. Took a little bit of a lag there, but that's going to be the formula that we want to use, and it's asking us to find the value of the 10th term in the sequence. So a sub 1, just like before, is the first term, which is 3. Our common ratio we said was times 4, and then n minus 1 is going to stay as n minus 1. And then in this case, since I'm looking for the 10th term, I want to go ahead and plug in 10 for n. So I get 3 times 4 to the power of 9, because if I do 10 minus 1, I'm going to get 9. And don't forget when you're solving to follow your order of operations, so you want to do 3 times whatever 4 times 9 is. In this case, it's going to be a pretty large number, with 262,144. After I do the exponent, then I want to multiply by 3, and just bear with me, I get 786,432. So the 10th term in this sequence is that number there. Definitely a larger number than what we got in the arithmetic because we are using an exponent, so our numbers are getting a lot larger. Alright, so at the bottom of this page we have a couple of more examples. It says Detective McMurlock is looking for some traffic information for the highway leading into town. The x-coordinate is the month, so we have 1, 2, 3, 4, just like normal, and the y-coordinate is the average speed in miles per hour. Help McMurlock use an explicit formula, so now we have to use explicit, which includes the first term, not the recursive. So I'm going to take a look at these numbers, 75, 72, 75, 70, 57, and then 68, 45, and I got to figure out whether it's going to be an arithmetic or a geometric sequence. It looks like to me it's subtracting, maybe, it's decreasing, or we're multiplying by some sort of a fraction or a decimal. And if I actually go and I try to subtract all of these through, I'm not going to come up with the same number every single time, so it can't be arithmetic. It's going to have to be a geometric sequence. Now here's how we would verify that. So I'm going to use the trick that we kind of did before where I take the second term divided by the first term. So I'm going to take 72.75 divided by 75. And what we end up getting is 0.97, so that's definitely going to be a geometric sequence. And I didn't show the work here, but if I go all the way through, it's going to be geometric. The first term is 75. As we could see, the common ratio, so I circled ratio, is 0.97. Now, to write the explicit formula, we have to go back to what we talked about in the beginning of class. I want to go ahead and take a sub n, or f of n, however you want to think about it, equals my first term. So whether you say a sub 1 or f of 1, it's still the first term, which is going to be 75, times my ratio to the power of n minus 1. So then when I write that out, it's going to be 75 times the 0.97, or 0.97, however you want to write it, to the power of n minus 1. Now it says use the explicit formula to find the average speed on the 12th month. So just like we've been doing, instead of n, I'm going to go ahead and plug in 12 because that's what we're looking for, is the 12th month. And then you want to make sure, as always, that you follow your order of operations and you do your exponent first. So we want to do 0.97 to the power of 11 first, and then we're going to multiply it by 75. So when we do 0.97 to the power of 11, we end up with pretty long decimal, but rounded, it's going to be approximately 0.72. Multiply that to 75, and for our final answer, we end up with 53.65 miles per hour as our average. And for example number 2, we have a city convention center has been bringing in truckloads of chairs. They're setting them up along the front row of the stage. The first row has 10 chairs. Each row has 2 more chairs than that, and we want to find out how many chairs will be in the 24th row. So something like I always suggest you guys to do is make some sort of a little table or just organize your numbers. So in the first row we have 10. In the second row we're going to have 12 because we're just going to keep adding on 2. It says 2 more each time. 3 is going to get us 14, the fourth row is 16, and so on and so forth. Now the key word here is just 2 more then. It doesn't say 2 times more, so it's not going to be geometric. This is going to be an arithmetic sequence. So in order to find the 24th row, I'm going to take f of 24 equals the first term. So remember the first term always goes first, so the first term is going to be 10, plus the common difference, which we know is 2, and then times n minus 1. So I'm going to take 10 plus 2 times 23, because that's going to be 24 minus 1, no need to write that out. And then just don't forget your order of operations. You want to multiply 2 times 23 first to get 46, and then go ahead and add 10, which is going to get you a final answer of 56 chairs. Alright guys, so next up on page 6 we have linear functions. Honestly, if you've made it this far, you're awesome, because I know this video is longer than the other ones, but I'm trying to do a little bit more in depth for you guys. So we have the cost of a cup of coffee in town has increased based on this function. So we have 0.05x plus 0.50, where x is measured in months. Detective McMurlock thinks that this is an arithmetic sequence, but he has to prove it, because nothing is valid without proof. So something that you might notice is that we have our 0.05x plus 0.50 should look pretty familiar to something that looks like y equals mx plus b, maybe, with our 0.05 being the changing number, so that's going to be our m, that's our rate of change, and 0.50 is our constant number, that's going to be our y-intercept essentially, that's the number that we start at, so it looks very similar to y equals mx plus b. What is known about arithmetic sequences? Well, we know that they increase or decrease by a common difference, so you have to be adding or subtracting, and they're also limited to domain of integers. So you can't have a domain or any number that you're plugging in that's something irrational or random like the number pi, but it has to be an integer, a typical number that you find on the number line. Then it says find some values for f of x. You must use more than 2 values. So in order to see and establish some sort of a pattern, we have to plug in numbers to see if they work. So we just go with 1 through 4. Those are pretty typical. If we plug in 1, we get 0.55, 2, 0.60, 3, we get 0.65, and then 4, we get 0.70. Now it is important to make sure that you use at least more than 2 to make sure you can establish some sort of a pattern. So now it says investigate the data to see if there's a common difference or a common ratio. Just like how we normally would we take the second minus the first, the third minus the second, and it looks like there is a common difference of 0.05. This honestly we could have guessed from in the beginning. It's the same as our constant rate of change value or our m value or our slope. They all mean the same. And here we have our example at the bottom of the page. So standing outside the convention center, Detective McMurlock and you take note of the rental cars in the parking lot. There were 5 cars in the lot when you arrived, so before you got there. More cars were arriving based on the function that you see, 2 times 2 to the power of x. That means the function for the cars in the parking lot is now the both of them combined with the plus 5 at the end. What can you prove about this function? So we need to I'm going to assume that this is probably going to be geometric in terms of a sequence. It has the exponential function part to it. It has an exponent, but we have to kind of work on it to prove it, just like we did in the previous problem by plugging in numbers, let's say 1, 2, 3, and 4. So if I go ahead and plug in 1 through 4, I'm going to do a little bit of mental math, not really write it all out for you guys, but if I plug in 1, I want to make sure I do the exponent first. So 2 to the power of 1 is 2, times 2 is 4, and then plus 5 is going to get me 9, so it should get me 9 for the first value. And I'm going to follow that same process. So I'm going to take 2 to the power of 2 now, which is 4, times 2 is 8, plus 5 should get me 13. And then I'm going to go ahead and plug in 3. So 2 to the power of 3 is 8, times 2 is 16, plus 5 should be 21. And then 2 to the power of 4 is 16 times 2 is 32 plus 5 is 37. So that's what I get for the first couple of numbers that I plug in. And now I want to try to find a pattern between them. So I know that 9 plus 4 is 13, but it doesn't continue on and do plus 4 plus 4 plus 4. It changes. So we get plus 8 and then we get plus 16. So I'm going to try multiplication. Um, but it looks like if I do 13 divided by 9 and then 21 divided by 13 and then 37 divided by 21, nothing really works the way it should work. So I'm going to go ahead and say that this is going to be neither because it doesn't follow an arithmetic pattern nor does it follow a geometric pattern, so it's truly going to be neither. So here we are, page 7. I don't know what happened to question 1, but it is what it is. So here I have the table 1500 to 1400. It looks like he's definitely losing 50 calories per day. So the common difference is going to be minus 50. And then moving on towards question 3, we have our table here. We have the years and then the population of frogs. And it's talking about the recursive formula here. So it looks like from year 1 to 2 to 3 to 4, we have 25 to 20 to 15 to 10. And to me, that looks like a really clear pattern of subtracting by 5 frogs per every single year. So as we subtract by 5, we can hopefully realize that that is our common difference, and it asks for a recursive formula. So please keep in mind that whenever you're using a recursive formula, there is no first term. You only use either the common difference or the common ratio. All right, and wrapping it up on page 7 with question number 4. So you'll see we have years 1, 2, 3, 4. So that's pretty typical with the X values. And then you have amounts of mosquitoes at a local pond. So we start with 5, 10, 20, and then go to 40. What you'll notice that I just drew in green is that this isn't a straight line like the last graph was. It does follow a curve. And as we start to try to find that pattern from 5 to 10, we see times 2, and then times 2 from 10 to 20, and then times 2 again from 20 to 40. So if I'm writing a recursive formula, that means I want to take my common ratio in this case times f of n minus 1. You do not want to use the first term. And whether or not you have the times 2 in the front or whether you flip it to the back, just like the question answer has it here, it doesn't matter because multiplication, it doesn't matter the order that you do it in. Now on page 8, we've got question number 1. Create an explicit formula for the sequence below. So first we have to make sure and try to figure out what is the pattern that's happening here and whether it's arithmetic or whether it's geometric. So I'm going to go from 180 to 156.6 and so on and so forth. I'm going to notice pretty much here that it's not going to be arithmetic because if I'm subtracting, my end number should remain constant to some point. So like 180 to 156 is approximately minus 14. But then if I subtract 14 again, it shouldn't be 136. So I can kind of use some of my number sense to figure that out. So I'm going to assume that this is going to be geometric, but I still have to prove it. So I'm going to use that little trick that we do where I take the second term divided by the first term, so 156.60 divided by 180. And then I want to keep going all the way through and check it, but just for time's sake, every single time you divide, you will get 0.87. So it looks like we do have a common ratio of that. Then we want to create the formula, so f of n equals, and it is explicit, so I'm going to start with the first term first, 180, times my common ratio, which is 0.87, to the power of n minus 1. And the question says we're looking for the amount of medication after 24 hours. So I'm going to go ahead and plug in 24 for n minus 1, 24 minus 1 is 23. So I get 180 times, and remember you want to do your exponent first. This is going to get me an interesting number, but it's about 0.04064. And then I want to multiply that by 180, so I get approximately 7.32 milligrams. All right, for question number 2, again, we want an explicit formula. Isabella posted a photo or a video of her dog online playing the piano. So it looks like on day 1, she got 1 view. On day 2, she got 5. On day 3, she got 25. And on day 4, she got 125. Excuse my very poorly drawn curve, but it looks like it's going to follow that exponential curve. And as I try to figure out what's happening from one number to the next, I'm going to notice that 1 to 5 to 25 to 125, we are multiplying by 5 for every single time we're going on a day. So day 1 to day 2 to day 3 to day 4. So when I'm writing the explicit formula, I do want the first term, so I'm going to start with f of n equals 1, because we just got one view on the first day, times my ratio, which is 5, to the power of n minus 1. Now the question is asking for the number of views on day 10, so 1 times 5 to the power of 9, because I'm going to do 10 minus 1, no need to do that again. Now 5 to the power of 9 in a calculator is going to be a pretty large number. So we're going to get the existing 1 times 195,312,5. So 1,953,125 views just after 9 days. And last but not least, question number 3. So analyze the given function and we have to prove whether it's geometric, arithmetic, or not a sequence at all, or neither like we did before. So we have Detective McMurlock. He was rewarded with $1,000 for his work and he placed the money in his savings account modeled by the function 1,000 times 1.03 to the power of x. Now that very much looks like a geometric sequence to me, because we have our beginning amount, which is $1,000, we have our multiplier 1.03, and then we have to the power of x. So there's no way that's going to be arithmetic, so it could really only be geometric or neither, but I still have to prove what it's going to be. So the way I'm going to do that is I'm going to go ahead and start by taking at least 1, 2, 3, maybe 4, and plugging that into the function. So I'm going to go ahead and plug in 1. I want to do the exponent first, so 1.03 to the power of 1 times 1,000 is 1,030. 1.03 to the power of 2 times 1,000 is 1,060.9. And then 1.03 to the power of 3, and then times 1,000 is going to be 1,092.73 approximately. And then 1.03 to the power of 4 times 1,000 is going to be 1125.51. Now, after I do all this work, I still need to figure out whether this is geometric. I need to prove it. So what I'm going to do is I'm going to take the second term divided by the first term. I'm going to do the little trick. So 1060.9 divided by 1030. Then I'm going to do the third term divided by the second, the fourth term divided by the third. I have to make sure that they all match. And just to save some time, they all do match, and it looks like my common ratio is just 1.03. Who'd have thought? That's my base. That is what I'm multiplying by. So since I got the same number when I divided second to the first, third to the second, fourth to the third, this is going to be a geometric sequence with a ratio of 1.03. Now, last but not least, page 9, we made it finally to the end after about 40 minutes or so. We have our little review page. I highly suggest that you keep all these formulas as kind of a little cheat sheet, especially as you're going through the quiz. I'm not condoning using notes or anything like that, but if you need them to help you, you can. You are at home, so use the resources that you have. As always, if you have any questions, guys, please let me know, and good luck. And if you made it to the end, thank you. I appreciate you, and thank you for watching.